And we're back with magnetic fields. In this video, we are going to look at the magnitude and the direction of the force applied to an electron beam or some kind of current by a magnetic field. Okay, and we're particularly interested when the velocity of this electron beam or current and the magnetic field, which we're indicating with a B, is parallel or perpendicular to the velocity. Okay? So, let's have a read. We've got a charged particle will experience a force when moving in a magnetic field. Okay? Charged particle will experience a force when moving in a magnetic field. This can be a positive charge or it could be a negative charge. Okay? For this particle to experience a force, the velocity, or at least a component of the velocity, must be perpendicular to the field. Okay? So, let's say I've got a proton and it's traveling towards the right. Okay? And let's say that it's traveling within a magnetic field. So I'll use another color. Let's say the magnetic field is green. Let's say the magnetic field is also pointing towards the right. Okay, try and imagine 3D. So it's sort of like the field is also, there's some arrows that are like deeper within the page also pointing to the right. Okay, so try and imagine in 3D. This proton will not experience a force because the velocity is parallel to the field lines. Okay, for this proton to experience a force from this field, it will need to be moving perpendicular to the field. So either the field will be pointing up or down. Okay, this will produce a force on this proton. Okay, because the field in green is perpendicular to the velocity in red. You could also have an orientation of the field that is either into or out of the page. So to indicate that, we'll just use a whole bunch of X's, okay, indicating that the field is going into the page at those points. And you can imagine, because this is a 3D situation, the red velocity vector is still perpendicular to the green field vectors. Okay, it's hard to show that, but you can imagine it. Okay, the fields are going into the page, the velocity is to the right. Yes, that's right angles. Try and do it with your fingers. Okay, we'll be at right angles. So we'll experience some kind of force. Okay, that needs to be the case. You could also have something like the following, where you have, let's use some colors. So let's say you've got the velocity of the proton going up that way, and you've got the field pointing towards the right, let's say. Okay? Will it experience a force? Yes, it will, because a component of the velocity is perpendicular to the field. Okay, if I split my velocity into horizontal and vertical components, notice that this vertical component of the velocity is perpendicular to the field. Okay, we've also got a horizontal component which doesn't contribute to this force. All right. According to the study design, though, you only have to deal with cases where the directions are perpendicular or parallel. You don't have to deal with sort of like these oblique angles. We'll look at a case at the end of the video, but for the most part, you won't have to, at least according to the study design. But I'm going to show you how to do it anyway, because who knows what can happen. All right. So we want to know the magnitude of this force. What size is the force? That's given by this equation here. F equals QVB. Okay, let's see that on bigger, more bold red letters. So magnetic force, Fm, equals Q times V times B. F is the force, obviously with units of newtons. Q is the charge of the particle. V is the velocity of the particle in meters per second. And B is we're using to indicate the strength of the magnetic field, which has units of Tesla, or just the letter T. Okay. All right. There you go. It's a very simple equation. You just got to make sure that the velocity is perpendicular to the field in order to use this equation. If the velocity is parallel to the field, you cannot use this equation. even if the velocity is pointing that way and the field is pointing that way, it's still parallel. Okay, they're just pointing in opposite directions, but they are still parallel, so this equation doesn't apply. You just say zero force. Okay, so let's do a couple of questions here. Okay, these are qualitative questions, not quantitative. There's not really any numbers we've got to work with. Because the equation's so simple, you're just multiplying three things together, so we're not going to do too much time on that. But we are going to analyze which one of these will experience a force. So which of the following charged particles will experience a force? So you just got to remember, there just has to be a component of the velocity that is perpendicular to the field. As long as you've got that, that particle will experience a force. Okay, in the first case, yes. Okay, this is right angles, so yes, it's going to experience a force. This one here, no, okay, because the velocity and the field are parallel. They're in the same direction. Okay, or not the direction, but, you know, there's no perpendicular component to them. This third one down here, bottom left, so we've got the velocity apparently going into the page. So imagine this proton just going straight down into the screen. And the field lines are pointing downwards. And yes, that is at right angles. Okay, that is perpendicular, so yes, it will experience a force. Finally, this last one here, okay, you've got a charged particle, but its velocity is zero. Okay, now, even if you could apply the equation, you'd see that, according to the equation, the force would be something times zero times something. So, no, it won't experience a force. Simply just placing a charge in a magnetic field is not enough for that charge to experience a force. Okay, it's not like electric fields where you can just place a charge in an electric field and it will experience a force. Magnetic fields are different. Okay, only moving charges experience a force, and they have to be moving in a certain way. Alright, so now we come back to the question, what if the charge is neither moving parallel nor perpendicular to the field? Okay, so that was that picture that I had over here. Okay, this picture here. What if the charge is not parallel or perpendicular? Okay, well, I hinted before that you have to work out the perpendicular component of that velocity. Okay, so what you do, split the velocity into components using trigonometry and determine the size of the perpendicular component of the velocity. And that's the value of v that you are then going to use in this equation here. Okay, so v is the perpendicular velocity. Let's do that in a question. Again, according to the study design, you don't need to know how to do this, but we're going to do it anyway. So, a proton enters a magnetic field of strength 10 Tesla at an angle of 60 degrees as shown in the picture below, at a velocity of 2 times 10 to the 6 meters per second. What is the magnitude of the force experienced by the particle? So we know that we've got a charge moving in a magnetic field. We're going to be using F equals QVB. We know Q, okay, it's a proton. It's got a charge of 1.6 times 10 to the negative 19. B is 10 Tesla. V, okay, that's the thing that's going to trick us here, okay, because it's not perpendicular. It's not moving perpendicular to the field. So what we've got to do is split it into components. It's got this component here, which is parallel to the field, and it's got this component here, which is perpendicular. Now, according to the information in the question, this here, this velocity arrow has a magnitude of 2 times 10 to the 6 meters per second. Okay. Because this angle here is 60 degrees, this angle here is also 60. All right, which means the perpendicular component of the velocity. Okay, well, if we use trig, I mean, you've got hypotenuse, you want adjacent, so you're going to be using cos. So this component will be 2 times 10 to the 6 times cos 60. There we go. All right. And if you use a calculator to do that, I haven't worked it out, so let's do it together. 2 times 10 to the 6 times cos 60. Oh, it's just 1 times 10 to the 6. Of course. I've put my physics hat on and forgot my method stuff. So that's 1 times 10 to the 6. Q, 1.6 times 10 to the negative 19, same as the charge of an electron. B is 10. Stick it all together. Force equals 1.6 times 10 to the negative 19 times 1 times 10 to the 6 times 10. Okay, or times 10 power of 1. If you add up all the powers of 10 together, you get negative 19 plus 6 plus 1. That's going to be negative 12, so you get 1.6 times 10 to the negative 12. Okay, just double check because I probably went wrong somewhere. Nope, all good. 10 to negative 12. So there you go. Okay, not too hard. I don't know why they don't include that in the study design. Maybe they just think there's way too much stuff going on. But there you go. Okay, you just split it into the perpendicular component, work out what that is using trig, and use that as your value for v in the question. Otherwise, if it's perpendicular, you just use that value of v given to you straight away. If it's parallel, force is 0. Okay, cool. So that's it. We'll stop there, and I'll see you in the next video.